Now, Ohm's law can actually be thought of from two perspectives. It can be thought of from the perspective that I mentioned last time, how voltage and resistance means there's more current. Or it can be thought of as sort of the other way around, where if I know the amount of current that's going to flow through the material and I know the amount of resistance, I'm going to know the amount of voltage drop. In other words, if I have a resistive material, let's say R, and I have a certain amount of current that flows through it, well, the amount of voltage, this voltage, that's going to drop is going to be a very linear function. So the voltage is going to drop smoothly as it flows from the left to the right. And this is true for metals, but this isn't true for every material, and I'll tell you why. So metals, as I talked from the very first video, has this property where all of the energy bands of the electrons all blend together, and there's sort of this sea of electron effect in metals. But for insulators and semiconductors, this is not true, because what ends up happening is lower energy levels blend together, but then higher energy levels blend together differently from the lower ones, leaving this gap of energy right here. And we call this the band gap. So this is band 1, and we're going to call this the valence band. And this is band 2, we're going to call this the conduction band. And so this space between here is called the band gap. And for semiconductors, this gap is small. But for most materials like insulators, this gap is very large. What's interesting about semiconductors and this gap, though, is that we can use this gap to our advantage, because this gap in energy sort of can be thought of as a very precise amount of voltage drop. Let's say 0.7 volts, electron volts, because each electron is dropping in energy. And, different materials are going to have different energy band gaps. So some materials are going to have 1.8 volts, some are going to have 2.1 volts. It all depends on the chemistry of the material. So what does this mean? Well, nothing by itself. So if you just have a piece of semiconductor, nothing's going to happen. But you can take semiconductors and make special devices like LEDs, diodes, transistors, which are the building blocks of modern computing. I'm going to explain real quick how, for example, a diode works. What you do is you take one material, we call this the N-type material down here, and what this N-type material does is that its band gap is going to be the same size as this material's band gap, but this N-type material is going to be slightly lower in energy. So it's going to be slightly lower than this left material called the P-type material. What ends up happening is that when electrons flow from, let's say, this side to the left, the electrons are going to sort of pass on through the conduction band up here, but some of the electrons are actually going to fall down into this gap on the P side material. Now, what happens is that since they fall down into this gap, and this gap is always a very precise size due to the chemistry of the material, let's say 0.7 volts, that means the electrons will always lose exactly 0.7 volts as they drop from this side to this side. And so this is really useful in a lot of things like LEDs. For example, if you know that you lose exactly 0.7 volts as you go from this side of the material to the other, well, that means that there's always going to be a specific amount of energy. And since light has a certain amount of energy depending on its color, you're always going to get a very precise color coming out of this material. So, for example, red LEDs are typically 1.8 volts because the amount of energy from 1.8 volt drop makes a red light appear, and green LEDs and blue LEDs, so I guess I'll just write blue here, they typically have a larger drop of maybe like 2.1 volts. More energy means that it's going to be a different color from the more energy will mean that the more blue the color is.